Welcome to the 13th lecture of module 4. In this module, we are discussing reactor design. Before going to this lecture, let us have brief recap on our previous lecture. In the last lecture, we have covered graphical design procedure for the reactor size, and then we have seen how to construct rate, conversion and temperature chart. So, rate, conversion and temperature chart is basically plot of conversion versus temperature at different rates, which we call it contour plot, where 3 parameters are plotted in 2 dimension. In this lecture, we will consider material and energy balances in batch reactor. The brief lecture outline are as follows. We will consider total mass balance in batch reactor, material balance in batch reactor, then we will consider energy balance in batch reactor, enthalpy temperature relationship, and finally, we will consider adiabatic operation. So, let us start with batch reactor, general balance on the quantity under consideration. So, as we have already discussed the reactor design at the beginning of this module, to how to design a batch reactor for a single reaction, and we have considered a generalized transport equations or the balance equation. Like if we consider rate of accumulation of a certain components inside the reactor, that means accumulation terms. So, accumulation would be equal to rate of transport into the control volume, that is we can call it in, minus rate of transport out of the control volume, which is out, plus the rate of production within the control volume. So, we can write simply production. Now, the transport in and transport out, which is little bit artificial, but if we can call together, is the net rate of transport into the control volume, then that would be much better. So, we can write in terms of net rate of transport. So, we can write rate of accumulation within the control volume which would be equal to net rate of transport into the control volume plus rate of production within the control volume. So, now if we consider batch reactor, and first we will consider multiple reaction which is happening inside the reactor, and we will develop the generalized balance equation which can be simplified to the single reaction. So, let us consider an insulated system. Well mixed batch reactor, and volume is equal to V, in which there are m number of chemical reactions. So, chemical reactions one to m and n number of species. So, chemical species say J is equal to 1, 2, and here I can say I is equal to 1 to m, J is equal to 1 to n. So, n number of chemical species, m number of chemical reactions are happening inside a batch reactor. The reactor is well insulated and it is well mixed, whose volume is V. Now, if we write the balance equation, total mass balance equation in a batch reactor, we can write. So, this is our batch reactor and it is well insulated, where we have incorporated some chemical species and chemical reactants, and they will react and forming different species through several chemical reactions. So, we can write the net flow rate of mass into reactor. So, this net flow rate means in and out. So, since batch reactor we used to include the material inside, close it and then stir it for a certain period of time. So, there is no inlet or outlet. So, the net rate of mass into the reactor would be 0. Now, rate of production of mass within the chemical reactions would be also 0, as we have seen earlier that the mass is conserved in any chemical reactions if there is not huge change in energy like in nuclear reactions, where mass change is significant due to the evolution of heat, huge amount of heat. So, in this case, even if we have considered highly exothermic reaction of combustion, and where heat is evolved to a quite significant amount, but the mass change is not so significant, because that is with respect to the mass of the chemicals we use is negligible. So, rate of production of mass within the reactor would be 0. The rate of accumulation of mass within the reactor would be equal to, if V is the volume and if we consider the density, rho is equal to the density of the fluid, then the mass would be rho V. So, the rate of accumulation of mass within the reactor would be d rho V dt. So, rho V is the total mass within the reactor, and if we write the balance equation, so accumulation would be equal to net rate of mass into the reactor and rate of production of mass within the reactor. So, we can write d rho V dt is equal to 0, which simply says that the mass inside the reactor is constant, or from here we can say that rho V is equal to constant. The mass inside the reactor is constant. So, this is the total material balance equation in a batch reactor. Now, let us do the species mole balance. Now, if we write for any species, say kth species, chemical species, so we will consider kth chemical species and we can write net flow rate of kth species into the reactor is equal to 0. The rate of production of kth species within the reactor would be, V is the volume of the reactor and there are m number of reactions going on. So, I is equal to summation over I is equal to 1 to m alpha I k r I. So, the alpha I k is the stoichiometric coefficient of the chemical species. So, this is the rate of production of kth species within the reactor. Now, rate of accumulation of kth species within the reactor this would be d V into say C k is the concentration of species k dt, and which we can write would be equal to V d C k dt, since V is equal to constant. So, we are considering constant volume system. So, here V is equal to constant. So, we can take out the V from the differential sign. So, V dck dt. So, if we write the balance equation, we would obtain V dck dt would be equal to 0 plus V summation over I is equal to 1 to m alpha I k r I. So, from here we can write, so V will cancelled out. So, we will get dck dt would be equal to summation over I is equal to 1 to m alpha I k r I. So, this is the familiar batch reactor species balance equation, or we can say batch reactor rate equation. So, now we will consider the enthalpy balance equations. We have seen the how to calculate for a single reaction, how to calculate the heat of reaction from the thermodynamics, and how the heat of reaction is related with temperature. We have seen that. So, now we will consider the enthalpy balance for a particular reactor, that is batch reactor, and as we have considered the reactor is well insulated. So, enthalpy balance insulated reactor, so we can write net flow rate of enthalpy into the reactor this would be 0 since it is well insulated. Then rate of production of enthalpy within the reactor should be 0, and rate of accumulation of enthalpy within the reactor would be d rho v h cap dt. So, h cap is the specific enthalpy that means it is enthalpy per unit mass. Rho v is the mass of the fluid or the reactant and h cap is the enthalpy per unit mass. So, this is change of enthalpy with respect to time. So, now if we write the balance equation, we would get d rho v h cap dt would be equal to the net rate of enthalpy into the reactor is 0 and this is also 0. So, it would be 0. So, from here we can write rho v h cap is equal to constant, and from the total mass balance we have seen rho v is equal to constant from total mass balance So, from here we can write H, the enthalpy H cap specific enthalpy is constant. So, this is not so trivial as it first appear, as we are much more concerned about the change in temperature instead of enthalpy. So, let us see how the enthalpy is related with the temperature. So, enthalpy temperature relation. So, we are usually interested is in the temperature rather than enthalpy, and we will try to write the specific enthalpy in terms of the temperature. And then we would see that the relationship between enthalpy and temperature will depend on the composition in the reactor. That means, different species have different enthalpies which is defined relative to some reference species and conditions. So, if we write total enthalpy per unit volume of an ideal mixtures of n species. So, total enthalpy per unit volume of an ideal mixture of n species we can write rho h cap would be equal to summation over k is equal to 1 to n C k h k bar. Here h k bar is the partial molar enthalpy and Ck is the molar concentration of species K. Now, if we consider 0 heat of mixing as we have considered ideal solution. So, for ideal solution we can assume zero heat of mixing. And also assume constant specific heat for each species. So, then we can write in terms of temperature rho h cap is equal to summation over k is equal to 1 to n Ck h f k plus C p k T minus T reference. H f k is the molar heat of formation and Cpk is the molar heat capacity of species K. Cpk is the molar heat capacity of species K. T is the temperature and T ref is the reference temperature at which the heats of formations are defined. So, this relation of enthalpy temperature is a drastic simplification of the different situations where small change in enthalpy is of great importance, like in case of many gas phase reactions, the small change in enthalpy can change, no. So, gas phase reactions, the enthalpy change is much larger compared to the heat of mixing. So, there should be error due to the assumption of constant specific heat. Now, so we have rho H cap is equal to summation over K is equal to 1 to N C K H F K plus C P K T minus T reference. Now, if we simplify this, this would be rho H cap would be equal to summation over K is equal to 1 to N C K C P K into T minus T reference, which plus summation over K is equal to 1 to N C K H F K. So, the sum of the term of the heat capacities, we can write the specific heat of the whole mixture, because this is from K is equal to 1 to N for N species. So, we can write from here, we can write this would be equal to rho C P cap T minus T reference plus summation over K is equal to 1 to N C K H F K. So, here we have considered the sum of the terms involving the heat capacities at specific heat of whole mixture. And we call it as CP cap. So, now if we take the time derivative of it of this relation, so we have rho H cap is equal to rho Cp cap T minus T reference plus summation over K is equal to 1 to N Ck H F K. Now, if we take the derivative of this and put into the differential form and assume Cp cap is independent of both temperature and composition. So, this is another big assumptions. Specific heat of the whole mixture is independent of both temperature and composition. Now, if we take the derivative of this would be d rho h cap dt would be equal to rho Cp cap dt by dt plus summation over k is equal to 1 to n h f k d c k dt which we can write is equal to rho Cp cap dt dt plus summation over k is equal to 1 to n h f k d c k dt from the species balance we have obtained d c k dt is equal to summation over I is equal to 1 to m alpha I k r I. So, if we substitute this over here, this would be summation over I is equal to 1 to m alpha I k r I. Now, we have d rho h cap dt is equal to rho Cp cap dt dt plus summation over k is equal to 1 to n h f k summation over I is equal to 1 to m alpha I k r I. Now, if we reverse the order of the summation, we can write from here d rho h cap dt would be equal to rho Cp cap d of temperature d of time plus summation over I is equal to 1 to m r I into h f k alpha I k. So, this will be summation over this. So, this term the summation over heat of formation H f k times the stoichiometric coefficient for the m number of chemical reactions can be recognized as the heat of reactions, which is the definition of the heat of the reaction. So, from the definition, the heat of reaction sum of the heat of formation times the stoichiometric coefficient this is the heat of reaction. So, we can write from here d rho h cap dt would be equal to rho Cp cap d temperature by dt time. So, dt by dt plus summation over I is equal to 1 to m delta H I heat of reaction into R I. So, this relation of energy balance or enthalpy balance simply say that the temperature in the reactor will rise or fall due to heat released or taken by the chemical reaction. So, this relations will tell whether the temperature of the reactor will increase or it will fall due to the heat released or taken by the chemical reaction. Now, if we write for the adiabatic system the relations which we have developed, that is, now from the enthalpy balance we know that d rho H cap dt is equal to 0. So, if we substitute in this relation d rho H cap dt would be equal to rho Cp cap dt by dt plus summation over I is equal to 1 to m delta H I R I. So, this term from the total enthalpy balance, this is 0. Now, if we substitute this is 0, we can write rho Cp cap dt by dt would be equal to summation over I is equal to 1 to m minus delta H I R I. So, this relation simply said that the temperature in the reactor will rise or fall due to heat released or taken by the chemical reaction. Now, this derivation is basically for adiabatic well insulated systems. Adiabatic well insulated system. Now, if we consider there is some net heat flux to this system, say QH, then the energy balance equation, if there is some net heat flux, say QH, which is into the reactor. So, the energy balance equation D rho V H cap dt should be QH. Now, since V is constant, we can write D rho H cap dt would be QH by V. Since V is constant. So, in the earlier balance equation, that is D rho H cap dt is equal to rho Cp cap dt by dt plus summation over I is equal to 1 to m delta Hi Ri. Here this term is QH by V. So, if we substitute here, this would be QH by V would be equal to rho Cp cap dt by dt plus summation over I is equal to 1 to m delta Hi Ri, and from here we can write rho Cp cap dt by dt would be equal to summation over I is equal to 1 to m minus delta Hi Ri plus Q H by V. So, this is the equation of the reactor temperature. Now, if this heat flux is happening across a surface whose area is A, so heat transfer across a surface of area A from a thermal reservoir at temperature T. So, we can write this relation rho Cp cap dt by dt would be equal to summation over I is equal to 1 to m minus delta Hi Ri plus Hf into A into the temperature difference. This is a T reservoir is Tr minus T divided by V. So, Hf is the heat transfer coefficient. So, most of the reactors are non-isothermal reactors, and this is the important case which we need to consider, because for adiabatic reactor, when there is no heat in or heat out, the adiabatic operation is often desirable, because there is little utilities we need to know incorporate, and it should be very easy to know operate during its normal operation. So, as we have seen, for the constant volume non isothermal batch reactor, we have two balance equation. One is for species balance, that is dCk dt is equal to summation over I is equal to 1 to m alpha I k r I, and adiabatic systems we have energy balance rho Cp cap dt would be equal to summation over I is equal to 1 to m minus delta H I R I. So, as we know, the rate of a chemical reactions is depends on both the temperature and the concentration, but this temperature dependency of the Arrhenius relation of the rate constant is quite nonlinear in nature. So, this is a case of initial value problems and can be solved, as we have discussed before, for the initial value problems for the integration. So, this is initial value problem. And the equations are strongly nonlinear in nature due to Arrhenius temperature dependency of rate coefficients. Now, if we consider single reaction and adiabatic operation, so we can write the species balance equation. Say we have dCk dt is equal to summation over I is equal to 1 to m alpha I k r I. For single reaction, we can write dCa dt is equal to minus Ra for the reactants. So, A is the limiting reactant. Similarly, the temperature relations rho Cp cap d temperature dt would be equal to summation over I is equal to 1 to m minus delta Hi Ri. This we can write rho Cp cap dt by dt is equal to minus delta H reaction into Ra. Now, from these two relation for the single reaction, if we equate rate Ra, so we would obtain from these two relations, say this is 1 and this is 2. So, from 1 and 2 we can get minus dCA dt would be equal to rho Cp cap divided by delta H reaction into dt by dt. So, this gives the this is the relation between temperature and concentration. So, relation between temperature and reactant concentration. Now, if we integrate this relation, so we have minus dCA dt is equal to rho Cp cap by minus delta H reaction dt by dt. Initial conditions T is equal to T naught Ca is equal to Ca naught at T is equal to 0. So, if we integrate with this relation, we would get Ca naught minus Ca would be equal to rho Cp cap by minus delta H reaction into T minus T naught, or we can write T minus T naught is equal to minus delta H reaction divided by rho Cp cap Ca naught minus Ca. Now, from this relation, from this second relation, this relation, we can derive the adiabatic reaction temperature. The adiabatic reaction temperature T adiabatic, if we define, this is the temperature which is achieved if the reaction goes to completion, that is Ca is equal to 0 adiabatically. That means, the temperature achieved if the reaction goes to completion adiabatically. So, we have T minus T naught is equal to minus delta H reaction divided by rho Cp cap into Ca naught minus Ca. So, for adiabatic reaction temperature, Ca should goes to completion 0 and T can be written as T adiabatic. So, we from here we can write T adiabatic would be equal to T naught plus minus delta H reaction divided by rho Cp cap into Ca naught. Now, if the reaction is reversible in nature, for reversible reaction, we can write T adiabatic would be equal to T naught plus minus delta H reaction by rho Cp cap Ca naught minus Ca equilibrium. So, for adiabatic reaction, for reversible reaction, the adiabatic reaction temperature would be the temperature at which the reactants attains the equilibrium concentration. So, this is very trickier to calculate the adiabatic reaction temperature for the reversible reaction, because the equilibrium concentration will change with the temperature. So, this is the equation for the single reactions, irreversible reaction, and for this single reaction the expression is Ca is equal to Ca naught minus rho Cp cap by minus delta H reaction into T minus T naught. This is for adiabatic batch reactor single reaction. So, now this can be substituted in the energy balance equation. We know the energy balance equation, rho Cp cap dt by dt is equal to minus delta H reaction into Ra. So, Ra is the function of concentration and temperature. So, if we substitute this red equation in case of the concentration, so these relations would be substituting say this is equation 3 and this is equation 4. So, if we substitute equation 3 in equation 4 in the rate expression, then this equation, the second equation 4 will be only the function of temperature. So, equation 4 would be only the function of temperature. So, this can be integrated to obtain temperature as a function of time, temperature as a function of time. So, in general this whole set of equations can be solved numerically to obtain the concentration and temperature profile. So, thank you very much for attending this lecture, and we will continue our discussion on the batch reactor balance equations, the reactor design equations, both in particularly emphasis should be given on the energy balance equations, and we will continue in our next lecture. Thank you.